See, the second thing in the addition of hydrogen halides is free radical mechanism. Right? Free radical mechanism, or you can also say anti-Markovnikov effect. Somebody entered in. Okay. Anti-Markovnikov addition. Okay. Let me first give you the equation taking propene. Propene with the same hydrogen bromide. In fact, peroxide effect or this anti-Markovnikov effect, or is also known as Kharash effect. It is observed only with HBr. I'll tell you why after the mechanism. Okay. In the presence of peroxide, you know the major product is N-propyl bromide. Exactly opposite to what you have seen earlier. So this is N-propyl bromide. N-propyl bromide is major here. Then the isopropyl bromide. Okay, this is minor. Now, major is because of anti-Markovnikov addition, also known as peroxide effect or Kharash effect. Okay, and actually this goes via a more stable free radical. Okay, now let us see the mechanism. So in the mechanism, there are 3 steps. The first one is chain initiation. Let us consider a peroxide. So this is benzoyl. Look at this. This is benzoyl peroxide. Now this benzoyl peroxide, in the presence of sunlight or UV light, undergoes homolytic fission. You all know this. So this homolytic fission leaves 1 electron to the bonded atoms, gives 1 electron. So we get C6H5, C double bond O, then O free radical. 2 such free radicals, right? Now let us consider the free radical. Okay, come on. Again, the same homolytic fission. I told you that this is called fish hook arrow, which refers to homolytic fission. Then, okay, C6H5. Then let me actually show you this. This gets an odd electron. Now form a bond between these two. You will be left with C6H5 free radical and carbon dioxide. Now this C6H5 free radical will combine with the hydrogen halide HBr. Even here also we get free radicals this way. Come on, add these two, right? So we get benzene, just a second, C6H6 plus, of course, the bromine free radical. Now this is chain initiation. Benzoyl peroxide in the presence of sunlight forms bromine free radical in the final step after reacting with HBr. Now the second step is chain propagation. Okay. See, in chain propagation, I have two steps. Now in the first step, we got bromine free radical. It is now going to get connected to propene. Let's see what happens. Propene with the bromine free radical. Okay, very interesting. Concentrate on this. See, you get two free radicals this way. I mean, the two carbons get odd electrons. We'll have two possibilities now. See, these two may combine. Let this be possibility A. Otherwise, even this. So this is possibility B. Hope this is okay. Only to give you clarity on this. Come on. When you go for A, this is what you get. CH3, the free radical will still be there. Then the CH2, Br. A gives this because in A, CH2 and Br get connected. So this is actually giving rise to a 2-degree free radical, right? See, this 2-degree free radical, of course, is a more stable one. Let us see the second case. B. Come on. CH3. Now the middle carbon forms a bond with bromine free radical. Now this is a primary free radical, right? A 1 degree free radical is a less stable when compared to 2 degree, right? Now let us take the second step in chain propagation itself. The free radicals formed in the first step now get hydrogen free radicals. Let me consider the more stable one, the 2 degree free radical, right? Now this 2 degree free radical with the HBr again. Come on. Go for homolytic fission again. This, oh, 1 second. You get free radicals this way. Come on, connect the two. These two. That's it. You get this. CH3, CH2, CH2, Br. Of course, a bromine free radical, which will again go into that first step. So that is the reason why we call this chain propagation. Hope this is clear. Now you have considered the secondary free radical, which is a more stable one, ended up with N-propyl bromide. Of course, got so many free radicals. Now in chain termination step, as usual, any two free radicals may combine. Let's see. Third one. Chain termination. Any two free radicals. Maybe the two bromine free radicals. When these two combine, of course, we get a bond between them. Bromine, Br2 is what we get. Now, if the secondary free radical formed in the first step of the chain propagation combines with the bromine free radical, we also get this dihalo compound, right? Now even this kind of free radicals may combine. Let's see that. This plus this one, right? That's it. A fresh bond is formed. You can show the bonds. These two, or say these two, then of course these two combine. A fresh bond is formed. Come on, CH3, then CH, this CH2Br, then this one. CH2Br. Okay, so any two free radicals combine to give different kinds of products. This is chain termination. Now, very important thing is I told you that peroxide effect or the anti-Markovnikov effect or the Kharash effect is observed only with HBr. Why not with HF, HCl, HI? Why only with HBr? Let's see. See, sometimes they give HCl with peroxide, but even with peroxide, when you consider HCl, remember you get Markovnikov product only, because no peroxide effect with these three. Peroxide effect is observed only with HBr. Even if you consider HI peroxide, no, just go for Markovnikov. Okay, only with HBr. A very important point to be remembered. But why? See, we have seen the propagation step, which has again got two sub-steps in that. That is where the interesting thing lies. Now with HBr, both the propagation steps are exothermic. Right? With HBr, both the propagation steps are exothermic. We know from the knowledge of thermodynamics very clearly that reactions which are exothermic in nature occur on their own, because we need not supply anything, isn't it? Now, then what is the problem with HF, HCl and HI? You know, with HF and HCl, second propagation step is endothermic. A very important point. First one is okay. First one is exothermic. But the problem is with second step. Whenever a particular step, a reaction is endothermic, see, it occurs only when heat is supplied. So that is the problem with HF. The second propagation step is endothermic with HF and HCl, but with HI, the first propagation step is endothermic. Second is okay, but first is endothermic. So remember, with these two, the second one, 2 second, 1 first. That is how you can remember without any confusion. With HF and HCl, second propagation step is endothermic, whereas with HI, the first one is endothermic, but with HBr, both the steps are exothermic. This is very interesting. Okay. Now the next one. This is of course a very interesting reaction. Addition of water. We can actually go in 3 different ways for adding water. One is acid catalyzed hydration. The second one is OMDM. I mean oxymercuration, demercuration. The third one is HBO. Nothing but hydroboration oxidation. Right? Let us first go for acid catalyzed hydration. Okay. Now, remember one thing in acid catalyzed hydration. Of course, I'll give you the mechanism. But let us first go for the basic reaction. Acid catalyzed hydration, or else simple dilute sulfuric acid. One thing I would actually like to say is dilute sulfuric acid adds water, whereas concentrated sulfuric acid removes water. Dilute is a hydrating agent, concentrated is a dehydrating agent. Okay. Now, the product that we get here is isopropyl alcohol. Let me give you the mechanism. Then we'll tell you one very important point. Come on. Propene. Let me consider H3O plus, because we know that H plus has got no independent existence in water. It exists in the form of H3O plus. Reason why I've taken H3O plus rather than going for H plus. But of course here I can actually take H plus simply. Can of course be shown this way straight away. You take it this way. And of course this goes like this. The water molecule is eliminated and literally we are using H plus. H without the bonded pair. Right? But see, for clarity's sake, would actually like to give this. Come on. Let us make the mechanism this way. See, I got a positive charge on a secondary carbon, a better thing, right? Straight away, of course, can be shown as I have actually shown in the previous way, or else you can do this. Will give you some more clarity. Even straight away, this can be taken this way, as shown previously. Now, what happens? Okay, water molecule is last. Then, of course, a secondary carbocation is what we got. You know, whenever a carbocation is the intermediate, we know that rearrangements occur. So these two are very important. Carbocation is the intermediate, so rearrangements are very much possible. Now add water. See, the first step is adding H plus. In fact, it is the acid catalyst that we have added. See the next step. Okay, yes, this one. Attack of the base. No, attack of the nucleophile, because the lone pair is given to a carbon with positive charge. I cannot say that the water is acting as a base, it is acting as a nucleophile. Now, what do we get? Come on. O, H still has a pair of electron. So a positive charge, because oxygen has got only 5 electrons around it, right? That means one short of what it has to have. Now then, the last step. Come on. Bond comes this way to the rescue of the positive charge, and H plus is last. You got your product. So that is the mechanism. Interesting thing is, you have utilized an acid catalyst in the first step. You have eliminated the same. In fact, that is the role of a catalyst. Enters in one step of the mechanism and goes out in the other step. Right? It is never used up quantitatively in a chemical reaction. Finally, would like to say just one point. That in acid catalyzed hydration, consider these two things. Markovnikov addition, along with that rearrangement. Markovnikov addition, nothing but regio, direction specific. You have to form a positive charge on the secondary carbon, because here you got 2 degree and 1 degree. Go for the 2 degree one, because it gives you the more stable carbocation. Don't go for the primary one. So that gives us the regiochemistry. Of course, because the intermediate is carbocation, you will always have rearrangement. We'll take one example.